Welcome to Lab 4, where we will be discovering DC and RC circuits. In this lab, we will be simulating simple series and parallel circuits, determining the behaviors of capacitors, resistors, and other circuit components, and calculating the time to discharge a capacitor. Some important concepts for this lab include Ohm's law, which states that the voltage is equal to the current times resistant, the node rule, which states that the current in is the same as the current out, the voltage of a capacitor, which is the charge times the distance between the plates divided by E naught times the area, the capacitance equation, and the loop rule, which states the sum of all voltage differences in a loop equals zero, and the time constant, which solves for the time it takes to discharge a capacitor to 1 over E of its initial charge. For Lab A, we use two batteries in series connected to two capacitors and two ammeters. The theoretical current for before and after the capacitors should both be 0.2 amps, as that is our voltage divided by our total resistance, and our experiment shows that. It's the same when the ammeters are reversed. When going around the loop, the sum of all delta V's should be 0. After the 100 ohm resistor, it's negative 2.04 volts. After the 47 ohm resistor, it's negative 0.96 volts, and our delta V from the batteries is 3 volts. When you add these together, you get 0, which satisfies our rule. If we replace the ammeter with a voltmeter, that causes an open circuit, which is why our ammeter reads 0 amps of current, as the current is not flowing. Using our readings from our last slide, we can calculate the resistance of the wire, ammeter, and resistors. For the 47 ohm resistor, we actually get a resistance of 48 ohms, and for the 100 ohm resistor, we get a resistance of 102 ohms. The resistance in the ammeter and wire are both 0. This is because they have 0 effective resistance, because it is a simulation. We also put an ammeter in parallel with the 100 ohm resistor. This raised the current to 0.06 amps. This is because the effective resistance is less because our ammeter has 0 resistance. Therefore, the current is traveling faster. We also did a potential versus position graph that shows the potential voltage between different points in the graph. As you go through the batteries, this voltage increases and stays steady until you get to the first resistor where it decreases, and then hits the second resistor where it decreases to 0, as our total voltage across the loop must be 0. In Lab B, we connected a light bulb, a capacitor, and a battery together in a circuit. When first connected, the light bulb is bright, then dims over time as the capacitor charges up and the current slows, until it eventually comes to a stop. When discharging a capacitor, the light bulb starts bright, just like before, and dims as capacitor loses charge and the current again slows to 0. The time to charge the capacitor with a 10 ohm bulb is 7.2 seconds. The time to discharge was 15.77 seconds. The time to charge with the 20 ohm bulb was 12.9 seconds, and the time to discharge was 23.1 seconds. We then use this data over 20 seconds to calculate the time constant by doing 1 over the slope of our line. Our expected value is 6 seconds, as that is our resistance times capacitance. Our experimental value gives us 6.02 seconds, and some potential error include getting error in the timings and potential calculation errors. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected real circuits you hooked it up to? A real ammeter has resistance, so the voltage would be lower and our readings would be different. What if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the current? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? The ideal model would have our capacitor be charged instantaneously, but a real wire has some resistance to it. In our simulation, our wires had 0 resistance, so in the formula, there is no time to charge the capacitor because there is no resistance. But because our wires in real life have resistance, there would be some amount of time, and it would be slower than our expected result based on our simulation. In conclusion, we learned the various effects of various components in the circuit. Thanks for watching.